Online exercise 2, part 2. Problem 1 from transport processes and separation process principles, 5th edition by Christy John Copolis, A. Allen Herschel, and Daniel H. Lepek. 26.4-5. Rectification using a partially vaporized feed. A total feed of 200 mol per hour having an overall composition of 42 mol percent heptane and 58 mol percent ethylbenzene is to be fractioned at 101.3 kilopascal pressure to give a distillate containing 97 mol percent heptane and a bottom containing 1.1 mol percent heptane. Calculate the moles per hour distillate and bottoms. So for the manual solution, the first thing that we need to do in this problem is to determine the light and heavy key compound. So in this, the light key is heptane while the heavy key compound is ethylbenzene. Next, we determine the components of the distillate and bottom. Since in the problem we are given the value of heptane in both distillate and bottoms, so the light key do have 97% in distillate while it has a 1.1% bottoms. Then we subtract this value to 100. So we determine the value of heavy key compound and distillate, which is 3%, while the heavy key compound in the bottoms is 98.9%. Next, we get the overall material balance. So feed is equals to distillate plus bottoms. Since the value of feed is given, we have 200. Then equation 1 will be used in order for us to easily determine the value of distillate and bottoms. Next, we obtain the equation for the heptane material balance. Since everything is already given in the problem, the value of the feed, the mole fraction of heptane in the feed, and the distillate and the bottoms, we will just evaluate it and it will become equation 2. Now, substituting equation 1 to equation 2, we obtain the value of the distillate, which is 85.2972 mole per hour. Next, we will use the calculated value of D in order to evaluate it in equation 1. So the value of bottoms is 114.7028 mole per hour. So in the DW sim, this step is first simulation configuration in which we will add the compounds that is given in the problem. So in this problem, we will add heptane and ethylbenzene. Then choose Pang-Robinson as a property package. 3, select the desired units for the simulation. Then for the flow sheet, we add the shortcut distillation column, then input the parameters given in the problem. Problem two. So I find it hard to find a textbook problem related to absorption or stripping. I find it hard to answer it using WSM. So I decided to use the sample problem from Mom Eliza's lecture in separation process. However, in this problem, I change the values and I also change the required. So the gas mixture at 1.0 atm pressure containing air and carbon dioxide is contacted in a single stage mixer continuously with pure water at 293 Kelvin. The two exit gas and liquid streams reach equilibrium. The inlet gas flow rate is 200 kilomole per hour with a mole fraction of carbon dioxide which is equals to 0.20. The liquid flow rate entering is 400 kilomole per hour. Calculate the amounts of the two outlet phases. Assume that water does not evaporate in the gas phase. H is equals to 0.4142 times 10 raised to 4 atm per mole fraction. So for the manual solution, um, the The liquid inlet stream plus the vapor or gas inlet stream is equals to liquid outlet stream plus vapor outlet stream. So from this, since the value of the liquid inlet stream is 400 while the value of the vapor or gas inlet stream is 200, we have a total of 600 kilomole per hour. So in the solution, it's just kilomole since I use basis of 1 R. We assume that L prime is equals to 400 kilomole. Then V prime, in order to obtain the value of V prime, we will use the molar flow of the vapor inlet stream and the given mole fraction of carbon dioxide, in which V prime is equals to 160 kilomole. Then we will use this equation in order. After that, we will use this equation to obtain the value of the outlet vapor outlet stream, which is V prime over 1 minus Y1. In next, for the liquid outlet stream, we will use this equation, which is L prime over 1 minus X1. Unfortunately, we don't have the value for X1 and Y1, so we need to find it first in order to calculate the value of the outlet vapor and liquid stream. So using this equation L1 plus V1 equals 600, we substitute these two equations in this equation. So we have the final equation 400 minus 1, 400 over 1 minus x1 plus 160 over 1 minus 1 y1 equals 600. Next, since we are given the value of HB, we will use this equation. So y1 is equals to 0.142x times raised to the 4th power over 1x1. Then we will substitute this equation to our final equation, which is this one. And now we got this equation. So in this equation, we can now solve for x1, which is 1.464069 times 10 raised to negative 4. And we use the value of x1 in this equation in order to get y1, which is 0.1998. Once we obtain the value of x1 and y1, we will go back to this equation in order to solve for the outlets, vapor, and liquid stream. So V1 is equals to 199.9437 kilomole or kilomole per hour. L1 is equals to 400.05628 kilomole or kilomole per hour. For the DW sim, we follow the same steps in the previous problem. So in the simulation configuration, we add air, carbon dioxide, and water. We choose Peng Robinson as a property package and select the desired unit for our simulation. Then in the flow sheet, we add an absorption or stripping unit. Then we input all the parameters given in the problem. So in comparison, the amount we obtain using manual computation and DWC are quite close to each other. I think that DWC round the numbers up, but the values that we obtain are all quite similar from each other.